Hi, I'm Wallace Kelly, and in this video I'm going to introduce you to Book 2 of The Elements by Euclid. In Book 2, Euclid deals with the topic of what we know today as geometric algebra. So in this introduction, we're going to look at how to translate geometric operations into their modern-day algebraic equivalent. And we'll look specifically at Book 2, Proposition 1, to see what algebraic law it expresses. Recall that the climax of Book 1 was the proof of the Pythagorean theorem, where we learned that the square of the hypotenuse is equal to the sum of the squares on the other two sides of a right triangle. Algebraically, we could express that as c squared equals a squared plus b squared. Recall that the proof of Pythagorean's theorem was performed geometrically. In fact, this diagram may look familiar, where side A was squared by constructing a square on that side of the triangle. And similarly, side B had a square constructed on it, and the hypotenuse had a square constructed on it. And the proof was in showing that the area of the sides of the legs of the triangle equaled to the area of the square on the side of the hypotenuse. What we saw from this is that you can use geometric shapes to illustrate concepts that we may have already learned in algebra. For example, squaring a number, that term itself that we used when studying algebra comes from the geometry of a line segment having a square constructed on it. Consider another example. The example of calculating the area of a parallelogram. We calculate that area by multiplying its two sides. In a rectangle, that would be its base times its height. In other words, multiplication can be expressed as the area contained by two lengths. If I have one length here, which is of size x, and one length here, which is of size y, then geometrically, the area contained by those two segments is multiplication of x times y. Keep that in mind as we again reach back into our memories of algebra and remember this technique that you may have learned called FOIL. FOIL is an acronym that stands for first, outer, inner, last, and it refers to the task of multiplying two expressions like this, x plus y times x plus y. And we were taught that we can multiply the first, the x times the x, and add to that multiplication of the outer, that would be the x times the y, plus the inner, the x times the y, plus the last, that would be the y times the y. And we might even simplify this further and say this is x squared plus 2xy's, we have two of those, plus y squared. And the question is, could this be expressed and reasoned about, and could we make formal proofs about this using geometry? And of course, the answer is an emphatic yes. Not only could we do that, but that's how it was originally done. Book 2 expresses algebra geometrically. Well, what is algebra? Let's step back and ask ourselves, what is algebra? I did a quick web search and I found that algebra could be defined as the part of mathematics in which letters and other general symbols are used to represent numbers and quantities in formula and equations. Wikipedia gives a similar definition. Elementary algebra differs from arithmetic in the use of abstractions, such as using letters to stand for numbers that are either unknown or allowed to take on many values. We could use this definition to understand geometric algebra. Geometric algebra makes use of abstractions, such as using segments to stand for numbers that are either unknown or allowed to take on many values. So the big idea is that algebra was originally performed geometrically. In fact, what we know in algebra as variables, those are seen in geometry as segment lengths. And in algebra, when we look at adding two terms like x plus y, in geometry, we simply attach those two segments together. And in algebra, when we multiply two terms, such as x times y, that would be forming the area of the segments. Our modern mind is very accustomed to working with precise values. But the ancient mind was much more visual, and they worked more with shapes than with values. So let's return to this example that we mentioned a moment ago called FOIL, where we have two expressions, x plus y, and we're multiplying them together, and we found that according to our algebra class, that could be expressed as x squared plus 2xy plus y squared. Could this be expressed and reasoned about geometrically? Let me show you how you would do that. First, you would have a line segment that represents the distance or the value x. Then you would add to it a value y. So that would be another line segment directly adjacent to it of length y. So now this total length is the length x plus y. Well, what if we wanted to multiply x plus y times x plus y? Well, geometrically, the way that you do that is you form an area where you have a segment of length x and a segment of length y perpendicular to your original segments, and the area inside these two longer segments is the area of x plus y times x plus y. But notice that we can subdivide this larger area into 4 component parts. This region in the upper left-hand corner, the area inside this region is x times x because it's a square with x on each side. And this region in the lower right, it is a square with sides y, so its area is y squared. Then we have remaining these two areas on each side, and they have an area of xy because one side is of length x and one side is length y, and the same one with the one in the lower left-hand corner. But notice that what we've done is we've taken this area x plus y times x plus y, and we've subdivided it into parts x squared plus, and then we have two regions of size xy, and then we have one region of size y squared. And sure enough, this matches perfectly with the technique that we knew from algebra as FOIL. Let's look at a numerical example. Here I have a segment AC, which is of size 3, and a segment CB, which is of size 2. Now segment AB is the sum of those, so that would be 3 plus 2. But I've drawn these perpendicular to another pair of the same lengths. So the total area would be 3 plus 2 times 3 plus 2, or 5 times 5, or 25. But notice that area, the total area, consists of these 4 smaller ones. And so I also have an area of 3 times 3, that would be 9. I have two areas of size 2 by 3, and so that would be 6. So I have two of those, 2 times 3, 12 altogether. And then lastly, I have an area of size 4, which is the 2 squared. And so that's 4. And sure enough, 9 plus 12 plus 4 is 25. So that brings us to Book 2, Definition 1. And Book 2, Definition 1 defines the term contained by. And we'll see this in several of the propositions in Book 2. The definition says any rectangular parallelogram is said to be contained by the two straight lines containing the right angle. So we have here two straight lines, a straight line AD and a straight line AB, and we've put them perpendicular to each other such that this rectangle in the middle is said to be contained by those two lines. We'll see this terminology in the first proposition. The first proposition says, if there are two straight lines. So let's imagine what that would look like. If I have a straight line, I might call it A, and the reason I'm calling it A is because Euclid called it A in his book. Then Euclid described a second line, two straight lines. One of them is A, and one of them is BC. Then he states, if there are two straight lines and one of them is cut into any number of segments whatever. So again, we have our straight line A, we have our second straight line, BC, but this one is cut into a number of segments. And we'll cut it here at point D, and we'll cut it here at point E. So now BC has been cut into three segments, BD, DE, and EC. Next, proposition 1 says, then the rectangle contained by the two straight lines. But he says the rectangle contained by, and there's that definition that we saw, by the two straight lines. Well, what does that mean? What that means is if we translate and rotate A down to this point, such that we have the line segment A here, then we have a rectangle contained by the two straight lines A, B, C. And then Euclid continues. He says that that rectangle contained by the two straight lines equals the sum of the rectangles contained by the uncut straight line. The uncut straight line would be straight line A, and each of the segments being the ones that we just cut, BD, DE, and EC. And so he's referring to the fact that what we can do is we can look at the rectangle contained by A and BD, and we can look at the rectangle contained by A and DE, and then we can look at the rectangle contained by A and EC, and we end up with these three rectangles. And Euclid's conclusion is that these areas 1, 2, and 3, the sum of those is equal to the area contained by the larger rectangle. And so you may look at this and say, well, that's pretty obvious. What's the big deal? Well, the big deal is when you look at this algebraically. So what I'm saying is that this text from Book 1, Proposition 1, actually expresses a familiar algebraic law. Let's see what that is. Let's suppose that we represent the length of side A. We represent that as length x. And then we represent the segment BD as y1, the segment DE as y2, and this last segment in between E and C as y3. Then we can calculate the area of each of these regions. The area of this first one is size x times y1, and the area of this second one is x, y2, and the area of this third one is x, y3. And if we put together everything that we've learned, we see that x times y1 plus y2 plus y3, that would be the larger rectangle, the rectangle contained by A and BC, that is equal to the component parts. So that would be equal to x times y1 plus x times y2 plus x times y3. And sure enough, this is one of the first things we learned in algebra, and it's referred to as the distributive law. And the distributive law says that if you multiply a value by the sum of values, that is equal to the sum of the multiple of the individual values. That is pretty exciting. We just derived geometrically one of the fundamental laws of algebra. And so that brings us to the conclusion of the introduction to Book 2 of Euclid's Elements. We've seen that you can translate geometric operations into their familiar algebraic equivalents. We saw that in algebra we have variables, and in geometry we have line lengths. We have addition of terms in algebra, and in geometry we have line segments that can be placed adjacent to each other, or line segments that can be cut into individual segments. And we've seen that multiplication in algebra is equivalent to finding the area of a geometry. Finally, we looked at Book 2, Proposition 1, and saw that it is a geometric proof of the distributive law.